The last topic I want to discuss for Chapter 1 before we move on to actual chemistry topics in Chapter 2 is unit conversion. And I've already shown you some of this in lab last week. Unit conversion is also known as the factor label method or dimensional analysis. They all mean the same thing. So the general idea is pretty simple. You just take something in a certain unit, we'll just call it unit X. You multiply that by what's called a conversion factor, which is just a true statement, and it has the unit you want to cancel in the denominator. So this would cancel on the top and bottom, and you'd be converting unit X to unit Y. Conversion factors are, as I said, true statements. 1 foot equals 12 inches means two things: 1 foot over 12 inches or 12 inches over 1 foot. You write them as a fraction. 1 hour equals 60 minutes can be written as 1 hour over 60 minutes or 60 minutes over 1 hour. So again, the numerator is equal to the denominator, so these are just equal to 1, and therefore they don't really change anything other than the unit. So when you're solving a problem, the idea is to set up an equation so that all the unwanted units cancel. For instance, let's say you wanted to convert the length of a marathon in miles into kilometers. All you have to do is know the length of a marathon is 26.22 miles. That's your starting quantity. And think of a conversion factor that's a true statement that has miles in the denominator. Well, we know that 1 kilometer is equal to 0.6214 miles. And again, you'll see that the whole point is that to have miles, the unit you want to cancel, on the opposite side as it is in the conversion factor. So they're on opposite sides, it cancels, and you get 42.20 km. That's pretty straightforward. The nice thing about this method is you can do problems stepwise, or you can write as many conversion factors in a row as you want. So the strategy when you're solving problems where you have to use unit conversion is to identify the information given, and then think about the information you need to answer the question, and then think of relationships between what you know and the unknown answer. And then you can plan a series of steps with these conversion factors. And then you can solve the problem just with multiplication and division. And the other thing you should do before you even do the math is to make a ballpark estimate. Just make an estimate of what you think the answer should be. And then when you get your answer, then you can be confident that you did it correct. So let me show you a multi-step, a few examples of this. So let's say we wanted to calculate the how many miles are in a light year. So again, you think of the information you need to answer the question. You need to know how long a year is in various units, seconds, days, months, etc. And you have to know how fast light travels, right? Just like in that other problem I showed you on Canvas, where I converted the speed of light into how long it takes sunlight to reach the Earth. So let's think about how we would attack this problem. I've written down all the known information. 1 year is 365 days, 1 day is 24 hours, 1 hour is 60 minutes, 1 minute is 60 seconds, and the speed of light is 186,000 miles per second. It looks like it would be difficult to do. But if you think about the units that you want to have the answer to be in, you can almost work backwards from the solution, the units for the solution, to the given information, and you can work out a pathway that way. Now you can do this in steps, but I'll show you how you can do it just in one calculation. So what I would do, first of all, if I have to have miles on top of years, I look at what I know, and I see the only piece of information that has miles in the numerator is the speed of light. So that would be a logical place to start. So when you're showing calculations, it's a good idea to write them like fractions like this. So 186,000 miles per second would be your starting point. And now we want to get to miles per year. So we can just leave miles alone, and all we have to do now is convert seconds to years. Well, I don't think any of us really know how many seconds there are in a year, but I certainly know that in 1 minute there are 60 seconds. So the unit I'm trying to cancel, I told you in most cases is on the bottom in the conversion factor, because in this case we're converting unit X to unit Y. But in this case, the unit we're trying to, it's not always that way. It has to be on the opposite side. So seconds are here, minutes are here, and just write a true statement. 60 seconds is equal to 1 minute. So there my seconds unit cancel, and then just keep going. 60 minutes in 1 hour. Minutes on the top cancel with minutes on the bottom. There are 24 hours in 1 day. We're almost there. And there are 365 days in 1 year. And there you go. You're left with the units you want. Miles, everything else cancels over years. And that's what I was looking for. So if you crunch the numbers, 186,000 times 60 times 60 times 24 times 365 gives me 5.865. I'm just reading my calculator here. 696 times 10 to the 12th miles per year. Now, ask yourself this: can you write all those digits in your answer? So go back and look at what went into the calculation. Just like in the other problem where you're calculating the time it takes for sunlight to reach Earth, all these are true statements, so they have an infinite number of sig figs. This one is a measurement, so that will determine how many sig figs to be in our answer. That has 3, so we have to round this to 3 sig figs. We can keep the 5, the 8, and the 6, and then we look at the first digit we're throwing out, which is a 5, so we can round this up to 5.87 times 10 to the 12th miles per year. And it's okay if you write miles per year like this, or miles / year like that. That's fine. So that would be written, I believe that's 5.87 trillion miles. So you knew you'd get a long answer, because the question was, how many miles does light travel? How many miles in a light year? That's asking how many miles does light travel in a year. And since light travels so fast, every second, there's a lot of seconds in a year, so it makes sense that you would have a very, very large answer. Another type of problem you can do is, let's say you are going on a trip. Another example. You're going on a long trip and you want to calculate about how much will you spend on gas. So it's very simple to do. Let's say your trip, you know, you're going to go is 2,150 miles. And let's just say that your car gets 30 miles to the gallon. And let's just say the average price of gasoline around the United States where you're going is about $2.80 per gallon. I know that sounds a little high these days, but in other parts of the country it isn't as cheap as it is here. So let's just say the price of gasoline on average is $2.80. How would you calculate how much you're going to spend? Well, you could do some educated guesses, I guess, but why don't you just try converting units? If I asked you how much you're going to spend, how much will gas cost? That unit, think about the unit, that's going to be dollars. So that has to be in the numerator. The unit in the answer, the unit of the question always has to be in the numerator in all the calculations. So I could easily start with, it would make sense to just start with $2.80 per gallon, and then multiply by the fuel efficiency of the car. It's 30 miles per gallon, which means you'd write it like this: 1 gallon over 30 miles. So make sure you can keep that straight. Sometimes people think they should keep the 30 in the numerator no matter what, but that's written as 30 miles over a gallon, so if I flip it, it's still a true statement, so it's really equal to the number 1, this fraction, but it has the units and the numbers in the right place. So gallons cancels, and then the trip is going to be 2,150 miles. So that is in the numerator, that's in the denominator, they cancel. My unit of dollars is where I want it to be, so you would spend $2.80 times 2,150 divided by 30. You'd spend about, our answer should be, let's see, that's 3 sig figs. Let's just say that is 2 sig figs, 30 miles per gallon, $2.80. So the calculator is giving me 200.6666 repeating. So I should round the answer to about 2 sig figs. So you'd spend about 2.0 times 10 to the second dollars. $200 is the final answer. So I hope that gives you a good idea of how to do unit conversion problems. There's a type of problem I'll give you in the discussion that requires a little more thought. It's sort of the last, it's a challenge problem, but what I would encourage you to do is try the problems in the back of the book and see if you can solve at least the easier ones. The further you go back in the exercises later in the book, the harder they get. Why don't I just try one more with you, and that's exercise 1.75 in the textbook. And this says, I'm just reading here from the textbook, it says, if you have a package of aluminum foil that contains 50 square feet of foil, which weighs about 8 ounces, aluminum has a density of 2.70 grams per cubic centimeter. What is the approximate thickness of the foil in millimeters? So what I like to do is draw a picture. So I'm just going to draw a picture of a piece of foil. And the question was, how thick is the foil? So draw a rectangular prism, we call it. This is your aluminum foil. And then write down what you know, the given information. You know that there are 50 square feet of foil in the box, and the mass of the foil is 8 ounces. Notice they're not giving us nice, neat metric units. They're giving us units that we are all familiar with. And the density of aluminum, symbol AL, is equal to 2.70 grams per cubic centimeter. What's the thickness? So here's the question. What is this answer? What is that dimension? So how would you attack the problem? Where is your, what do you know? You have to find a dimension in, it says millimeters. You know the area, you know the density. What if you convert everything to metric units? If you don't know where to start, first get everything in metric units. So if you say, all right, 50, I put a point there to just to specify that has 2 sig figs. 50 square feet. Now let me convert that to square centimeters. So why am I thinking of doing that? Because I have cubic centimeters here in the density. If I get the area in square centimeters, then I can relate that to the thickness, because feet squared don't cancel with centimeters cubed. But centimeters squared cancel with centimeters cubed to give me a thickness in centimeters, which I can then convert to millimeters. But I also have to take into account the mass of the foil. We'll get to that. Let's first convert the area to square centimeters. So I don't know a direct relationship between feet and a metric unit, but I know a relationship between inches and centimeters. So why not convert square feet to square inches? Now this is something to be careful about. This is square feet. So that means I have to multiply it by 2 conversion factors, because inches over feet wouldn't do it. That would just be 1 foot unit, and it would only cancel with one of the units up here. I'd still have units of feet up here, so I have to have the unit of feet times feet to cancel with that. So I have to do that twice. Now I have to convert it to inches to centimeters, so 2.54 centimeters in 1 inch is an exact number, and I have to do that twice as well. Now you don't have to write it out twice like this. You could put it in parentheses with a square around it, just like you could do that here. You could put a parentheses around that and write squared as an exponent. So if you look, feet squared cancels with feet squared here, inches squared on the top cancels with inches squared on the bottom, and I'm left with square centimeters here. If you do that math, if you do the multiplication, what does it come out to be? Turns out to be a big number, 46,451.52. I have to round that to 2 sig figs, so I have to call it, it's about 46,000 square centimeters. All right, let's see, how does that help me? Well, I know the density and that, but I have that unit of grams. So why don't I take the mass of the foil and convert that to grams? So 8 ounces. Now I don't know a direct relationship between ounces and grams by heart, but I can look it up. If I looked it up on the internet or in your textbook, you'd find that there are 453.59 grams for every 16 ounces. So that would, ounces on top cancel with ounces on the bottom, and I'd have to 2 sig figs about 230 grams. Now I have to do a little bit of thinking to figure out how I'm going to get thickness. I know density. It might help to think of density in its fundamental terms. It's mass over volume. Now I know the mass, 230 grams, and I know the area of the foil, and I don't know the thickness of the foil. But the volume of foil, the volume of a piece of foil would be its length times its width times its thickness. So I already know the length times the width. That's the area. So volume can be re-expressed as area times thickness. And there I've finally introduced what I'm trying to solve into an equation. So now the rest is just algebra. Let me just call thickness T equals, I'm just going to solve this equation, D equals M over area times thickness for thickness. Put that over there, move D to the other side, so I have thickness equals mass over area times density. And I think I have everything known. I know the mass, I know the area, and I know the density. If you ever get stuck on how to solve a problem that appears to be difficult, just look at the units. Think about how all the units can cancel. How can you combine all the units that you know into and have them cancel with multiplication and division so that you get answers, the answer of the unit of the answer, sorry. So I have, it helps to just come up with a general equation like that. Think about solving it in general, then plug it in. If you try to carry through numbers through all this, it just gets really messy. So I would recommend highly that you just come up with a formula and then plug in at the end with the numbers. 2.70 grams per cubic centimeter is my density. Almost all the time, but not always, but most of the time, all the information you're given will be used to solve a problem, but not always. And if I do that, I get 230 divided by 46,000 divided by 2.7 to 2 sig figs. It's 0.001 0.09 centimeters. And I have to convert that to millimeters. The original question was, what's the thickness of the foil in millimeters? So take my thickness in centimeters, and I know there are 10 millimeters in every centimeter. Just look at a ruler and you'll see that. So it's actually just move the decimal 1 to the right, and my final answer is 0.019 millimeters. That is a somewhat of a challenging problem. So if you can do that, you can pretty much do any unit conversion problem in this course.